Traditional printed circuit boards exist for one specific reason: to strictly confine electrical signals along designated metallic pathways. The Microstrip Patch Antenna abandons that logic entirely. It is explicitly engineered to leak its signal into the surrounding air. The structure relies on three distinct layers: a conductive metallic patch on top, a thick dielectric substrate in the middle, and a solid metallic ground plane on the bottom. These three layers form the exact same foundation used in standard printed circuit board manufacturing. In practice, the modern circuit board on the left is drastically lighter and more compact than older vacuum tube arrays. Because of this incredibly low profile and weight, patch antennas are the standard choice for mobile phones, Wi-Fi routers, and aerospace payloads. They are even essential for telemetry tracking in high-velocity guided missiles, where aerodynamics severely limit exterior hardware. Most modern wireless hardware relies on this configuration, using precise copper geometry to transition electrical signals into propagating electromagnetic waves through intentional leaks. The engineer controls this circuit through specific physical dimensions. Looking top-down at the patch, we establish the length and the width. If we shift to a side profile view, we see the third critical dimension: the height or thickness of the substrate material. These dimensions divide the physical labor of the antenna. The length dictates the specific operating frequency the circuit will target. The width governs the input impedance and determines the total bandwidth capacity of the system. Yet the flat central surface of this copper patch is completely inactive in terms of broadcasting. It does not radiate the signal. Instead, radiation occurs exclusively at the two opposing edges along the width of the patch, leaving the length boundaries dark. Due to the fringing effect, internal electric fields at the extreme edges escape the copper, arching into the air before looping back to the ground. The highest fields carry enough energy to break free entirely, propagating outward into space as electromagnetic waves. To maximize this fringing, an engineer can lower the substrate's dielectric constant, increase the patch width, or increase the board height. Here, fringing is not an electrical defect to be minimized. It is the single physical mechanism that allows the microstrip antenna to transmit vital information. The fringing effect introduces a specific design variable. The electromagnetic wave must travel through two completely different materials at the same time. We have the dense dielectric substrate directly below the metallic patch, contrasted against the empty air sitting right above it. The fringing fields are cutting directly through both the dense substrate and the clear air. Because air has a dielectric constant of approximately 1, the antenna fields experience a blended environment. The signal feels an average density that is measurably lower than the pure substrate. To accurately model the circuit, we must apply our first mathematical correction, the effective dielectric constant. This blended environment causes a distinct physical distortion. The outward arch of the electric fields gives the patch an electrical footprint that is larger than the actual piece of copper. This requires a second mathematical correction to account for the extra reach of the fields, known as the length extension. The true operational length of the antenna is the physical length of the copper, plus 2 times that length extension to account for both radiating edges. An engineer cannot rely on a physical tape measure. To tune an RF signal perfectly, they must calculate and design for the invisible, effective dimensions created by the escaping electric fields. Let us move from theory to practical application. We need to design an antenna targeted for a precise 10 GHz frequency. This specification slide details our raw hardware constraints. Our target frequency is 10 GHz, our substrate dielectric constraint is 10.2, and the board height is 1.27 millimeters. Step 1 is calculating the width to establish the correct input impedance and operational bandwidth. By factoring in the speed of light and our substrate properties, the ideal width locks in at exactly 6.33 millimeters. Step 2 is calculating the effective dielectric constant, adjusting for the air and substrate mixture. The calculation outputs an effective constant of 8.09. This drop from 10.2 down to 8.09 proves mathematically that our fringing fields are heavily utilizing the empty air above the patch. Step 3 is finding the fringing length extension. We must determine the precise distance the fields will push past the edge of the copper. The calculation reveals an extension of roughly 0.5 millimeters of invisible electrical length on both sides. Finally, step 4 is calculating the true physical length. We take our target electrical length and subtract those invisible field extensions. This gives us our final geometric measurement. The solid copper must be cut to exactly 4.2 millimeters. By systematically accounting for the invisible fringing fields, an abstract 10 GHz target has been successfully translated into a highly precise principal copper footprint. Stepping back from the calculations to look at the physical result, the completed hardware seems quite unremarkable, and mathematically it is far from flawless. It has severe operational limits. It only radiates outward in a half plane. It handles low power, and it inevitably generates parasitic surface waves that couple with nearby circuits. But these technical flaws are balanced against massive physical advantages. It offers unparalleled small size, negligible weight, and virtually zero manufacturing cost when using standard printed circuit fabrication. That exceptional ratio of low cost to high precision is exactly why this specific design powers everything from portable Wi-Fi routers to orbital satellites. Radio frequency hardware design is a constant, rigorous battle of balancing manufacturing constraints against the unforgiving laws of electromagnetics. The microstrip antenna demonstrates that effective design does not always require exotic materials. It often relies on using math to manipulate simple geometry, converting a